In this video, I'm going to start talking about chemical reactions. And so in this video, I'll be talking about it in somewhat more general terms, though I will be using an example case to sort of illustrate what I'm talking about. But we'll be talking about reactions. And so in reactions, there are essentially three things that we are interested in. There is the mechanism, the thermodynamics, and the kinetics. And so the mechanism is the step-by-step description of which bonds break, in which new bonds form in order to give the observed product. And so, a lot of times in things like organic chemistry and biochemistry, you know what goes into a reaction and you know what comes out. And so it's about trying to determine what's actually going on sort of in that black box between reactants and products that is allowing the products to form and, allowing it to form in sort of the yield that you are seeing. And so we'll see in later videos that we can get like mixtures of products and things like that. And so we're interested in why we get, more of one kind of product than the other. And so that is where the mechanism comes in. And to kind of let my biochemist show through again, the mechanism is important in biochemistry because we want to know, for instance, like if we're trying to make a medication, like how to inhibit a certain reaction from occurring. And so understanding the mechanism is important for things like that. And in organic chemistry, which is going to be a lot more things like in industry, we want to know how to control uh, a reaction in certain ways. And so maybe allowing us to get more of one kind of product than another kind of product in order to control that. So understanding mechanism is important for that. The other thing is the thermodynamics, which, so this is the energy changes that accompany, and I put here, and drive chemical and physical transformations, and what determines the equilibrium. And so thermodynamics is very concerned with equilibrium. So thermodynamics is about like what kind of reaction is favorable. So are we going to get more products or more reactants? And so it's very concerned with equilibrium and which direction of a reaction is favorable. Then kinetics is how fast a particular reaction will occur under given conditions. And so, when it comes down to it, kinetics is just thermodynamics, but it's kind of looking at thermodynamics through a different lens. And the distinction here is important because there are different sort of factors involved in one, in the other, or, there are different factors in kinetics that we are concerned with specifically that don't really have to do with like the equilibrium or favorability of a reaction. And so that would be kind of the way I would think about these two things, is that kinetics is how fast something happens, thermodynamics is how favorable something is. And the example I often use is a diamond turning into graphite. And so a diamond turning into graphite is thermodynamically favorable, and so it's going to happen spontaneously. So without you or anybody else having to do anything to do it. It's just going to happen spontaneously. But it's kinetically a very slow reaction. And so that's why we have this distinction here between kinetics and thermodynamics, where we can say that thermodynamics is sort of the favorability of something happening, and kinetics is sort of the speed at which something happens. And so in this video, I'm going to go through these three things kind of in succession here. And so if we want to talk about mechanism a little bit more generally here, before we get into our example case. So When we talk about a mechanism and an arrow pushing mechanism in particular, what we want to do is look for our electrons on one species, and then we have an arrow that points at where the electrons are actually going. And so those electrons can take that hydrogen, and then the electrons from this bond will actually move onto this uh, chlorine here. And so our products will be a chloride ion. And so we have our 6 lone pairs that I already show on there, but now we're getting both electrons from that bond going onto it. And so we end up with that with a negative charge. And so the electrons from this water here went and took this hydrogen, and so it took the hydrogen positive ion. And so what we end up with is we have our water here, but now we also have another hydrogen. So I'll draw that right here because those electrons took it, and so now this is positively charged because we went from neutral and added this positively charged hydrogen onto it. And so we end up with our hydronium ion. And so kind of the take-home message here is that the arrow is always pointing in the direction that the electrons are moving. And I make this distinction because I've tutored students who are taking organic chemistry, and they wonder why we don't have the arrow going in the other direction. So why don't we go from the hydrogen onto here? And and this kind of gets to something that is a little bit, I guess, meta for this. So in a certain way, I am probably like the wrong kind of person to teach organic chemistry. And this is because organic chemistry is something that came very easy for me. And that's not to like try to brag about my intelligence. So for instance, when it comes to math, I really love math, but math is something that comes difficult for me. And so in a certain way, I am probably a better on this on YouTube here on this platform. I'm almost a better math teacher than an organic chemistry teacher because the math is something that I understand where people struggle with it. Because I struggle with it too, and so you know, when I finally understand something in math, it's something that I can go, oh, this really helped my understanding, and so I can sort of impart that on other people. Where organic chemistry, there is this sense where it's like a student is struggling with something, and because it came so easy for me, it's like, how is somebody struggling with this? I don't understand what's difficult about this. And so, I mean, I don't want to say that I'm going to be a bad organic chemistry teacher here, but from a certain angle, you could almost see why I would be a bad organic chemistry teacher from that angle. But so this is, you know, this idea of like the arrow pointing in the direction of electrons moving was just something that somebody had to say that to me once, and it was just like, okay, I understand. And like, you know, that's just how, you know, the way my brain will work from there on out. Where I've had students come in and they say, why don't we point in the direction of the hydrogen? And I think part of that is comes from in general chemistry when we do acid and base chemistry, we're always sort of talking about the way that the hydrogen ion is moving. So we're always interested. So an acid is something that donates a hydrogen to something, and a base is, you know, something that takes a hydrogen from something else. And so we're always sort of talking about it in terms of which way the hydrogen ion is moving, where then we get to organic chemistry, and now we're sort of going in the opposite direction. So the way I think about it is just we're always pointing in the direction that electrons are moving. So the arrow is always pointing in the direction that electrons are moving. So up here we have this lone pair here, and this is moving towards our hydrogen, where the electrons in this bond here are now moving onto our chlorine here. And so we end up with our chloride ion and our hydronium ion here. And so that is kind of my, I guess, advice or my way of trying to think about this, if this was something that was confusing to you, is that we're always we're always sort of pointing in the direction of the electrons here. And so on this one, we do this. So this lone pair on this ammonia uh, is going to move towards this hydrogen on this water, and so then the electrons from this bond are going to move onto that oxygen there, and so we end up with this right here, where we have this hydroxide ion plus now we have an ammonium here, which is going to have our our four hydrogens bound to it rather. So we end up with this, which will have a positive charge on it. And so, yeah, we're always pointing the arrow in the directions that electrons are moving. And so you could almost think about these electrons as like an arm that's sort of coming out to grab onto, say, in this case, it's a hydrogen. It's a hydrogen up here as well. So in this case, we are sort of talking about acid-base chemistry in these first two examples. We're talking about Bronsted-Lowry acid and base chemistry, where we have a base like this water here is acting as a base in this case, and this ammonia here is acting as a base in this case. And so this is another thing, and I think, I mean, I've made videos on acids and bases for general chemistry, my general chemistry playlist, and also my inorganic chemistry playlist, but I think I might make another one in this video series, because what we see here, and this is another thing I've found that students are confused with, is in this case, we have our water acting as a base, and in this case, we have our water acting as an acid. And so, like I said, I'm going to make a video on this for this playlist, I think. But for our purposes now, just know that whether something is acting as an acid or a base is very context dependent. And so in this case, we're adding in this hydrochloric acid, so we're adding an acid, so something that's a strong acid, and therefore our water is going to act as a base. Where here we're adding something that is, well, I wouldn't call it a strong base, but it's a stronger base than water. And so now our water is going to act as an acid. And so something acting as an acid or a base is context dependent, and it has to do with whether we're adding something that's a stronger acid or a stronger base. So they're relative to each other. So relative to water, this HCl here is a strong acid, and so the water will act as a base. Relative to this ammonia, water is a weak base, and so it will act more as an acid. But anyway, I don't want to get too much into that. If you at least understand that the strength of an acid or base is context dependent and that it's relative, you should understand that. So, like I said, I'll probably make a video that goes into that in a little bit more detail here in a couple videos. All right, then this mechanism here is one that might look a little strange now if you haven't seen things like this, but it's something you're going to be running into a lot in organic chemistry. So we take our lone pair, we have our arrow, and we're going to come at this carbon right here, this carbonyl carbon, and then we're going to have one of the double bonds, the electron pair from one of the double bonds go onto that oxygen there. So this carbon here has a partial positive because the oxygen is more electronegative, and so that has our partial negative, and so that's why this is going to come after that carbon. So we will end up with something that looks like this. So we have our CH3s here. We now have our oxygen here, and I'm not going to draw in the lone pairs just for the sake of time. And now we have that. And so again, we have our lone pairs or our electrons moving towards something, and so that is what the arrow is. And they're going to generally move towards something that it has a positive or a partial positive charge. And that actually gets into Lewis acids and Lewis bases, where uh, this is our Lewis acid here, and this is our Lewis base. And of course, this Lewis base here is also a Bronsted-Lowry base. And that just comes from the fact that Bronsted-Lowry acid and base chemistry is a specific example of Lewis acid and base chemistry, where Lewis acids and bases uh, are much more general than the Bronsted-Lowry acids and bases. But again, like I said, I'm going to get into that in more detail. I do have, like I said, videos on that in my general chemistry playlist and in my inorganic chemistry playlist. But I do want to make a video on that that is sort of more organic chemistry focused. And so the kind of acid and base chemistry we're going to be interested uh, in organic chemistry. But anyway, now we're going to actually move on to what this video is going to be talking about the most. So we're going to use this chlorination of methane as our sort of example reaction throughout this video. And so I talked about this in an earlier video very briefly. And so what we're doing is just adding chlorines onto this methane here. So we add a chlorine onto that, and this hydrogen here will go with the other chlorine to make HCl here. And so we do that sort of over and over again until we can sort of saturate our carbon with chlorines here, and always making these HCl's as a sort of byproduct here. And so a few things we can sort of infer from what's going on here is that chlorination does not occur at room temperature in the absence of light. And so we know the reaction requires energy to initiate it. So if you sort of know where that's going, that has to do with activation energy. So the best wavelength of light is a blue color that is absorbed by chlorine gas. And so we know that chlorine must be activated in order to react with methane. So it's the chlorine that needs to be activated here. Then the light-initiated reaction is a high quantum yield, which means that we can get many product molecules for every photon of light. So, you know, we get like hundreds of product molecules per photon of light. So as a result, our mechanism needs to explain how hundreds of reactions can occur from a single photon absorption. And so the best reaction for this is what is called a free radical chain reaction. And so we'll see that a free radical reaction is one that we're not actually going to focus on much in the organic chemistry, in this organic chemistry playlist, but we will see why we're going to use it for our example here, because we can well, it's going to be because it is what's called a homolytic cleavage, and so we can get the bond dissociation energies from it. But we will go through the mechanism here, and I'm going to go through it somewhat quickly. So a free radical chain reaction has an initiation step which generates the reactive intermediate, and I'll be talking a bit more about reactive intermediates in the next video after this one. Then we get the propagation steps. So the reactive intermediate reacts with a stable molecule to form a product and another reactive intermediate, so allowing chain reaction to continue. Then we get the termination steps, which are side reactions that destroy reactive intermediates and slow or stop the reaction. And so we will look at the initiation here. So remember, we have our blue light here. So H nu here being well, it's the formula for energy of light. So H and then nu. You might also see it as H bar and omega, which is just the angular frequency for this. But anyway, we have this coming in. It's going to break this bond, and what we see is we're forming we're forming free radicals. And so for that, we again follow the electrons, but now we use only a half arrow because we're going to have single electrons moving in. So one electron goes to one chlorine, the other goes to the other chlorine, and so we end up with a free radical here plus another free radical here, where a free radical is a single unpaired electron. So remember, in the above, we were looking at these lone pairs on electrons, the movement of lone pairs. And when we do that, we use the double-headed arrow. When we are looking at the movement of a single electron, we use the single-headed arrow, like what I have going on right here. And so we end up with these two species here that have a just single electron, not a lone pair. And that is called a free radical. So the single unpaired electron is called a free radical. And so you may have heard that in the context of like nutrition, where you want to take like antioxidants that are supposed to clear out free radicals. And the reason for that is because free radicals, which we produce in our bodies from oxygen, are extremely reactive. And so like in the body, they can start causing all kinds of damage if you don't get rid of them. So we have things like glutathione and things like that to get rid of free radicals in our body. But for now, we're using free radicals for our reaction here. And so we take one of these chlorines here, so we could kind of bring it down here. So now what we do, we take this one electron here, we do a single arrow there, we take this here, we do a single arrow there, then we can do that with a single arrow there. And so what we end up with is Cl to a hydrogen. So the bond, we're getting one electron from here and another one from this bond here. We're forming this hydrochloric acid. And then here we are forming a carbon, hydrogen, hydrogen, and now we have a free radical there. And so this one electron moved onto that carbon. So that's our first propagation. And so then our second propagation, we bring this product down here. And so now we have another free radical. We're going to go here. This one will come here, and this one will go here. And so now we have our C with our H's on it here with a Cl bound to it, and we have also produced another Cl here, which this Cl will then go back up here to react with another methane. And so we just have this, so that's why it's called a propagation step, because we are producing another part of our reactants up here in order to keep this reaction continuing. So continuing to flow through here. But then, of course, we have termination reactions, which are reactions that do not produce another one of our reactants up here. And so we can have this here where we have one electron coming from there, one coming from there, and we are also producing one of these, which is exactly what we are trying to produce in this step. So we are producing that. We can also have two of these coming together. So we have two of these coming together like this to produce our Cl, and we can have two of these coming together to produce an ethane here. And so this will produce an ethane from this reaction. And so we have one electron coming from there and one coming from there to form our bond. And so we see none of these are producing another one of our reactants here. And so that's why those are called termination steps. And you can also have these reacting, I mean, even with like the container that your reaction is occurring in. And so, and that's kind of a hallmark of these free radical reactions. They occur extremely fast, which again is why, like our in our body, we have like superoxide dismutase, which gets rid of the free radicals. And that has to be just an extremely fast enzyme to get rid of it because these reactions happen very fast. So well, it happens fast in the sense that as soon as a free radical is made, it's going to react with something. As we'll see when we get to the kinetics part of this video, uh, it's it's not fast, so this initiation step is not always very fast. So actually producing these free radicals is not necessarily fast. But once you produce the free radicals, then they react extremely fast. All right, so that is the mechanism, and so that's sort of the mechanism of our sort of example that we're going to be using here. So now we're going to get to that second part, which is thermodynamics. I'm not going to spend too much time talking about thermodynamics in general because I've already talked about that in like my general chemistry playlist, and I would assume that if you are watching these videos, you are at least in a 200 level organic chemistry class and so have covered this in your general chemistry. And so remember, we have our reaction here, and this is our equilibrium expression for it. And so for this example, we have our CH4 plus Cl2 going to CH3Cl and HCl, and this is actually our equilibrium for it. And we see this is a very large KEQ, and so this is a very favorable reaction. All right, and so then thermodynamically we can express KEQ as this. So this is our Gibbs free energy here. So if we just take the negative natural log of both sides and then do some rearranging, we end up with our delta G, or Gibbs free energy here, being equal to RT times the natural log of our KEQ. And we also know that our Gibbs free energy is equal to our enthalpy minus temperature times the change in entropy here. And so we can then put that into our KEQ here for our delta G. So we do a little bit of mathematical manipulation here for that, and we end up with this right here. And so we see that if our delta S is positive, then the numerator gets larger, and so our KEQ gets larger, and so it's product favored. Whereas if our delta H is positive here, then the denominator will get larger and our KEQ will get smaller, where then it's also the opposite, where if this delta H becomes negative, then this whole expression gets smaller, and so the denominator gets smaller, our quotient here gets larger, where the KEQ here is our quotient. And so for our purposes, we're mostly going to be concerned with the delta H, because the delta H is essentially a measure of the relative strength of bonding in the products versus the reactants. So if weaker bonds are broken and stronger bonds are formed, the reaction is exothermic, meaning that the delta H is negative. And so for chlorination of methane, the delta H is negative 105.1 kilojoules per mole. And so if stronger bonds are broken and weaker bonds are formed, the reaction is endothermic, so our delta H is positive. And in that case, then our T, our temperature times the change in entropy, will have to be greater than our change in enthalpy. So for chlorination of methane, the delta S is 12.1. Pay attention to the units here. This is joules per mole. We're up here, it's kilojoules per mole. So this is so far larger in magnitude than this is right here. And so that's kind of why we're sort of more interested in the delta H here. And so If we look at this for our chlorination of methane, so we have the negative 105.1 kilojoules per mole here for enthalpy. We're looking at sort of room temperature here, so about 298 Kelvin. And so this is then converted the entropy into kilojoules per mole. And so we end up with negative 109 kilojoules per mole. And so if you, when in your general chemistry, you may have seen a table that looks like this. So comparing sort of the positive delta H to negative delta H with positive delta S to negative delta S, where at high temperature, if we have a positive delta H and positive delta S at high temperature, we will have a negative delta G. And so it's therefore spontaneous. At low temperature, we have a positive delta G, and so therefore it's non-spontaneous. If we have a positive delta S and a negative delta H, then this will be spontaneous at any temperature. Whereas if we have positive delta H and negative delta S, then it's non-spontaneous at any temperature, which means non-spontaneous meaning that you would have to put energy in order to get a reaction out of it. Um, so yeah, then at negative delta H but negative delta S, then this is spontaneous at low temperatures and non-spontaneous at high temperatures. But anyway, we're going to sort of move over here. And so this is just looking at sort of the percent of products. So, products as a percentage of sort of total products and reactants. So we see when we're at positive delta G, it's only 17% product, so it's going to be mostly reactants. When we get up to 0 here, then we're at sort of 50-50. Then when we go into the negative, our K starts going up. So then the percentage of products starts going up here. So we can look at that graph here. So we have percentages on our y-axis and our delta G here on our x-axis, where this is flipped so that this side is positive delta G and this side is negative delta G here. And so we see that the percentage of products goes up as delta G becomes more negative. All right, so we can also look at what's called the bond dissociation enthalpies, or also known as bond dissociation energies. And so, we use BDE for this, and so, I have kind of, I guess, a dirty mind, and so I see BDE, my first thought is big dick energy, and so I will try not to say that as we go through this. So we call this bond dissociation enthalpies and bond dissociation energies. So energy, enthalpy, you can kind of use that interchangeably, but just remember it's bond dissociation. And so we're looking at sort of the energy that it takes to break bonds and make bonds. And so this is why we have been using the free radical reaction here for our example, even though free radical reactions are going to be sort of a very minor part of the reactions that we're going to look at throughout this playlist. And the reason is because it's what's called a homolytic cleavage, free radical. And so we do that rather than a heterolytic cleavage, which is the one where we're moving lone pairs around. Since these ones, the energy can be very solvent dependent. And so if we're thinking of a water here and we want to look at the breaking of this bond where we're going to have the electrons moving there, and so we end up with H plus and our OH minus. If we're doing this in a polar solvent, that's going to be a lot easier to do because we can have the polar solvent sort of help stabilize these charges, whereas if we're doing it in a nonpolar solvent, then it's going to be much more difficult to stabilize those charges. Whereas with a homolytic cleavage, so if we're doing like a homolytic cleavage of water, we are then going to an H with a free radical and an oxygen with a free radical. And in both cases, this is uncharged, and both of these are uncharged. And so it's a lot less solvent dependent. So that's why we use the homolytic cleavage to get the bond dissociation enthalpies. All right, so this is kind of an important point right here. Energy is consumed to break bonds, and energy is released upon bond formation. And I think this is one of those things that people have difficulty with, because when we think of like breaking something, so we have, we'll just use R and R here. We always think of like we break this bond, and it's sort of releasing energy as we break this bond. Then we have to sort of use energy to sort of take two things, and we have to like use energy to sort of paste them together into a bond. But that's not actually how things work thermodynamically. So the reason a bond forms is because it's energetically favorable. And so a bond is actually lower energy. A bond is lower energy than, having, something like this. So, the reason that a bond forms between these two things is because a bond is more energetically favorable. And things that are more energetically favorable are things that have less energy. And so this is an important point to always keep in mind, that energy is consumed to break bonds and released upon bond formation. And so we have here, so our delta H is the sum of all the bond dissociation energies of bonds broken minus the bond dissociation energy of bonds formed. So if we have something like this, so we have this AB bound together, this CD bound together, and we're sort of switching around so that we have AC bond together and BD bound together here. So we're looking at the bond dissociation energy of AB plus CD, so that's the bond dissociation energy of our reactants minus the bond dissociation energy of our products. So this is a table that is found in the book that I'm using, so the Organic Chemistry 7th edition by L.G. Wade. And so this just gives bond dissociation enthalpies, or energies, if you will, of these different bonds here. So they're showing the bonds here, so the HH, this would be deuterium, deuterium here, fluorine, fluorine, but then we have the carbon to hydrogen bonds, and carbon to these halogen bonds, and so on and so forth going on here. And so one thing you can notice here is that the bond dissociation energy of hydrogen to fluorine is higher than it is to chlorine, which is higher than to bromine, which is higher than to iodine here. All right, so we can look at the reactants here. So the reactants for our Cl-Cl bond, so in our chlorination of methane example, we have this as plus 242 kilojoules per mole. This is for this carbon to hydrogen is plus 434 kilojoules per mole. And so we get a total of 677 kilojoules per mole. Then our products, so these are the bonds we're forming. We have 431 kilojoules per mole and 351 kilojoules per mole for the hydrogen to chlorine and carbon to chlorine bonds respectively. And so we have 782 kilojoules per mole. So we put that in, so 677 minus 782, we get our negative 105 kilojoules per mole that we have been sort of saying throughout this, that I've been sort of using throughout this. That is the enthalpy of the reaction, and so that is the difference in the strength of the reactant bonds and the strength of the product bonds here. Where remember, negative is exothermic here, and so for our case, for our purposes here, because we have the delta G equaling the delta H minus T delta S, this is going to be a much bigger player in this, and so this is kind of telling us that the strength of the product bonds is stronger than the strength of the reactant bonds, and so therefore the product is energetically favorable. All right, so switching gears a little bit to kinetics, and again, this part right here is something I cover in more detail in other places, like in my general chemistry playlist, but we have our rate law here. So the rate is equal to this rate constant times the concentration of our two reactants here raised to these powers here, where these powers are giving the reaction order with respect to each of these reactants. And so the total reaction order is the sum of those two right there. And so to get those, you actually have to run experiments by sort of altering the concentrations of our reactants in order to get our rate law. But then we're going to zoom in a little bit on this rate constant here. And so the rate constant is given by this, which is the Arrhenius equation. And so we have A here times this E to the negative E sub A over RT, where this E sub A here is our activation energy. And so that is the minimum kinetic energy molecules must have to overcome the repulsions between electron clouds when they collide. And so when we heat something up, for instance, we have our two molecules here, and they're going to have an electron cloud that's negatively charged, and so they're coming at each other. They're going to repel each other. So you need enough kinetic energy. You need these coming at each other fast enough that they're going to collide and reactions can occur. And so that is what the activation energy is the minimum kinetic energy that these things have to be sort of moving at each other in order to overcome that repulsive force. So this e to the power of the negative activation energy over RT, where R is the gas constant, T is the temperature, is the fraction of molecules with the requisite energy to overcome the repulsions. Then this A here is the frequency of collisions. So it's going to be between 0 and 1, that A, and it's the frequency of collisions in the correct orientation for a reaction to occur. And so as we saw earlier, for instance, I used that example of the acetone here that has that oxygen, and I had the OH minus here coming towards it. So if this is coming at it from this direction or this direction, a reaction is not going to occur, but it has to come at it from that direction in order for that reaction to occur. And so the A is sort of the frequency of collisions that are in that correct orientation for a reaction to occur. And so we can look at this. So this is looking at the fraction of molecules having the correct energy here as a function of the kinetic energy. So the area under these two curves is the total number of molecules in our system. And so we see at 300 Kelvin, so the area is the area under the blue curve. And so we see this is our activation energy, and this sort of darker green here is the proportion of molecules that are at the correct kinetic energy here in order to react. Whereas if we raise it to 373 Kelvin, we now get this extra area under our curve. So it's the area under the red curve. And so we have this extra part right here. So that extra proportion of our molecules that are above that activation energy will therefore react. And so you may have seen these reaction coordinate diagrams in general chemistry. So we have the activation energy, which is the difference between the reactants here and what's called the transition state, which is sort of I guess the geometry and state of the molecules at that sort of highest energy point there. So the activation energy is the energy that's needed to sort of get over this hill here. So to get to the top of the hill and then be able to sort of fall back down this hill. then the delta H, which is the energy that will be released, so this is the reaction coordinate for an exothermic reaction, is going to be the difference between the reactant energy and the product energy. So remember the relative difference of the stability or strength of bonds between the products and the reactants here. And so we don't count the activation energy of that because that is a wash here. So we're adding energy in to get up there, and then we are releasing energy there. But this cancels out with that, and so it's a wash. And so the delta H is just the difference between the reactants and the products here. And so for our chlorination of hydrogen, this is our reaction coordinate. And we see we actually have two transition states. We have this one, which is the higher one, and so it's the rate limiting transition state, and then we have this transition state here. And so we have our methane here with our chlorine free radical right there. And so the reaction here is an H going to this chlorine here, and then the other electron going onto that carbon. So we end up with this free radical. This is going to sort of become HCl, and we're not concerned with that anymore. So we then bring in our Cl2, and so we have the homolytic cleavage here, or the bringing together of that electron, one from the Cl there, the other one going onto that Cl. So then we have our products right here, and so we have the chlorinated methane right there. And so the activation energy for this first step here is 17. We get up here, we go down to this right here. Then we have another activation energy, which is just 4 here, and that's going to be in kilojoules per mole there. So we go up there, and then we come back down here. And so we see this is +4, which gives us from here down to the products of -109. But because we had this +4 here, we end up with -105 as our net delta H here. And that is, again, the delta H that we've been using this entire time here. And so, yeah, that is the reaction coordinate for that. And so that is why this activation energy is part of our Arrhenius equation, which, remember, is this. And that is our Kr here, our rate constant, which was part of our rate law here, which is telling us how fast this reaction is going to go. And so how fast a reaction is going to go is, as we see, dependent on this activation energy here. And so then we can look at this for the halogenation of methane. So we've been looking at chlorination here, but we can also do fluorination, bromination, and iodination here. And so we see that for the fluorination, the activation energy is quite small. And so we can look at the relative rates here. So we have our E to the negative activation energy here over RT, and we're just sort of multiplying it by 10 to the 6 here just to get the numbers in a place that is a little bit more understandable. But what we see here is our relative rates, and so don't take these numbers too seriously as like anything sort of, I guess, meaningful in their absolute sense. We're looking at these in relative senses. And so we see here, like with the fluorination, we have this 140,000 at 300 Kelvin compared to 300,000 at 500 Kelvin. And so this is quite a bit faster at 500 Kelvin than it is at 300 Kelvin, which you would expect. You add energy, you can get over that activation energy much more easily. But then we see that this for fluorination is considerably higher than it is for chlorination. And so I said in an earlier video that the fluorination is extremely fast. The chlorination and bromination are relatively fast, but they're slow enough that you can have a little bit more control over them. Then the iodination here is extremely slow. And so we can see that in these relative rates here, where this is this huge 140,000. We go down several orders of magnitude to this at 300 Kelvin. Then we go down many more orders of magnitude to the bromination. Then this is extremely small for the iodination. So it's on the order of 10 to the negative 19 here. Then at 500 Kelvin, we have 18,000 here. We go down several orders of magnitude to this 0.015, which would be like 1.5 times 10 to the negative 2 there. Then this is down to 10 to the negative 9 right there. And so that is just looking at the relative rates sort of as a function of these activation energies. So this has 5 kilojoules, this goes up to 17, then 75, then 140 kilojoules as our activation energy for each of these. And we can see the effect that has on the relative rates. Then we are also changing this temperature here. And so between these two, we can see what effect the temperature has on the relative rates there, where this R here and this E here are just constants. So we can't really adjust those. But anyway, that is the kinetics there. And so again, just kind of summing up, the things we looked at in this video are the mechanism, the thermodynamics, and the kinetics. So the mechanism is just sort of the step-by-step arrow pushing process of what the electrons are actually doing, where they're going, what bonds are breaking, what bonds are forming. Thermodynamics has to do with what is actually favorable, and that gets into equilibrium. So is the reaction going from reactants to products going to be favorable? And so is it going to be spontaneous, or is it something that you have to sort of put energy in to actually do? Then kinetics is the rate at which a reaction will occur. And as we saw, that is a function of the activation energy and the temperature. It's also a function, as you would see in the rate law equation that I showed, it's a function of the concentration of the reactants as well. But our purposes here, we were looking at sort of the activation energy and the temperature. The activation energy, as we saw, is a function of the transition state, so how high the transition state is. So the activation energy, if the transition state was up here, we'd need more activation energy. If it was down here, we'd need less activation energy. And you may remember, for instance, from general chemistry, if you put a catalyst in there that's actually lowering the activation energy by making the transition state more stable. So it helps stabilize the transition state and lower the activation energy. But anyway, I don't want to ramble on too long. This video is already getting quite lengthy. I will be talking a bit more about reactions in the next video, and so we'll be looking at things like reaction intermediates and sort of the stability of transition states and reaction intermediates and how that is important for the way that a reaction happens. And so it's important for sort of all three of these aspects of reactions. But anyway, I hope you found this video helpful, and I will see you in the next one.